We present joint work with title is changing the fiber multiplier of an attractive invariant test for a
I will. Okay, thank you for the introduction, Felix. Thank you very much for the introduction. I'm happy to be back in Bell Level and have a chance to talk this time about another topic. I'm working with Nuria in my PhD, particularly an application of quasi-conformal surgery to the context of quasi-periodically forced maps, QPF maps from now on. So let me first say that quasi-periodically forced maps naturally appear in nonlinear dynamical systems when considering like a stroboscopic map, that is a point carrier map, but using a section in time for flows which are driven by a quasi-periodic forcing with several incommensurate frequencies. So in the real setting, people are especially looking for strange non-chaotic attractors, which appear like in the regions between chaos and order, and they can be observed in some nonlinear electric circuits. But here we are interested in the dynamics of the complexification of these QPF maps, which can be seen as fiber holomorphic maps over an irrational rotation of the circle by an angle, say alpha, between 0 and 1. To be more precise, we say that a QPF holomorphic map is a continuous screw product of this form, where in the first coordinate we have an irrational rotation, and in the second one we have an holomorphic map, the fibers map. So when you, as usual, we are going to be interested in the long-term behavior of arbitrary points under the iteration of this capital F, whose end iterate is given by this composition of holomorphic maps. And well, as advanced by Nuria in yesterday's talk, this is a non-autonomous dynamical system. So the the function in each iteration depends on the fiber that is on the angle. So we usually we like to imagine this like in a sort of three-dimensional space where we have the torus like with 0 identified with 1, and in each fiber we place like a complex plane which gets maps to a complex plane in the fiber theta plus alpha, and so on. So if we have a point here Z, well, in 2 coordinates, then this is mapped by F to the corresponding F point in the complex plane of theta Z. And then we go to alpha plus 2 alpha and so on until we cover densely the torus. So observe that here we don't have fixed points or periodic orbits. So we may ask which are the simplest invariant objects in this case. And they turn out to be these continuous curves, whose graph is invariant under our map capital F, our quasi-periodic map. So these are the ones that satisfy this function, and they will look like something like this, which is one periodic, right? So here precisely this point get maps to the one in the next fiber, and so on. Okay, so we are assuming that that our QPF map is injective in a neighborhood of this invariant curve. So that means that the critical curves that are defined by the zeros of the derivative of our fiber maps along the fibers do not intersect our invariant curve gamma. So, and then without loss of generality, we can place this invariant curve at 0 just by a non-autonomous translation, right? So from now on, we imagine that gamma is exactly 0. okay, for simplicity. And then in order to study the local dynamics of this QPF map around this invariant curve, we introduced a fiber multiplier map, which is basically a complex version of the Lyapunov exponent in the complex direction for this invariant curve, which recall that is basically that it tells you the exponential rate of separation of points arbitrarily close to this invariant curve gamma. And here we also have like the imaginary part correspond to kind of a rotation number. But I just want to mention that this factor, this exponential, in terms of the winding number of the derivative, which we call the index of gamma, makes this logarithm well defined because it kind of undoes the number of terms of the derivative. And in particular, we are going to say that gamma is an attracting invariant curve if the multiplier has modulus less than 1, or equivalently if the Lyapunov exponent is negative as usual. And we denote its basing by this calligraphic A, which will appear afterwards. So for simplicity, we are going, although we can study more general QPF polynomials, here today, let me focus in this quadratic family, Q lambda, in which our results are stronger. So the fiber maps here are just lambda z plus z squared, but here lambda is a continuous curve which lives in this space of loops which avoid the origin. So we have kind of a well-defined index for the invariant curve. In this setting, following the work by Sester, who laid the basis of fiber polynomials over a compact set, we define the fiber Julia set, a field-in Julia set, as usual. No, the points in this kind of three-dimensional space with bounded orbit. And indeed, it can be seen that these are completely invariant sets and also full compact sets, as well as its fibers denoted by K sub theta. So in particular, we are interested in the situation where where the critical, the unique critical curve is completely containing the attracting basin of 0. So we can say that it's kind of hyperbolic in the sense of Sester. And then we have 0 as indeed the unique attracting curve for our family, for our quadratic map in this family. And the set value map, like theta goes to the fiber of the field in Julia set at zeta, is Hausdorff continuous. And and in this setting, the fibers are going to be indeed quasi-disk. So we can think like that this lambda is kind of in a generalized main caryot in the sense of the step. And more importantly, for our later purposes, the boundaries are going to be of 0 Lebesgue measure for all theta. Okay. So our goal is to kind of generalize the classical quasi-conformal surgery of changing the multiplier of an attracting cycle, which was introduced by Sullivan in a seminar in 1981 to prove that the multiplier map that goes from a hyperbolic component to the unique disk is a conformal isomorphism. So let me call by kappa tilde the fiber multiplier map, which assigns, I mean, here if for our family, it assigns to, yeah. Can see this, yeah. So it assigns to each parameter, to each loop, the multiplier of the invariant curve at 0 for this quadratic map Q sub lambda. No, that in this case it will be the exponential of this logarithm. And taking into account this factor. Okay. So this goes, from this infinite dimensional space to the puncture disk. So here we aim to show that given an initial fiber map, an initial multiplier in the unit disk, K naught, there is a simply connected neighborhood in which we can find kind of a right inverse tilde lambda, which goes back to this infinite dimensional space of closed curves avoiding the origin. And we want to show that this is indeed an embedding, so an homomorphism onto its image. And for this purpose, we have first to bring here a fiber version of the well-known conics linearization theorem, which is due to Mario Ponce in 2007, who uses this natural notion of conjugacy for these QPF maps. So just let me say that two quasi-periodically forced maps F and G are going to be conjugates if there is a continuous map H of this form, where the fiber maps are homomorphisms in some domain, and that makes the diagram commute, and so does the iterate. So just to make notice that we are doing this non-autonomous iteration. So here I just display how it acts like in each fiber, in each slice of your original domain. And let me notice that the fiber map is going to be preserved under conformal conjugacies, which satisfy this kind of topological property, which is going to be the case in our construction. So, here, like in a more general setting, we're just considering a quasi-periodically forced holomorphic map with an attracting invariant curve of index M and fiber multiplier kappa. Ponce showed that there is kind of an invariant, an open invariant tube, like call it T, in which the dynamics of your map is kind of conformally conjugate to a linear contracting QPF map. So indeed, in this setting, we can say even more if the frequency alpha is Diophantine, because then using this result by Nuria Fageya, Angel Jorba, Mark Jorba, I mean, not his son, but his PhD student, and Giancarlo Stagier, they showed that F is indeed conformally conjugate to a nice linear skew product of this form, where kappa records the fiber multiplier. And the fiber conformal map psi, it preserves the origin in this setting and makes the diagram commute. So now we are ready to present like the surgery construction for our quadratic family. So basically, as we were saying, in this neighborhood of kappa naught, which we call here U, we want to find a fiber quasi-conformal map. That is, each fiber map is quasi-conformal, such that it depends continually on theta and also on kappa, and which conjugate this initial quadratic polynomial Q sub lambda naught to a new map Q lambda kappa which has an attracting invariant curve of 5 multiplier kappa. And basically, the proof goes as follow a sketch like we fix this kappa to start with, and we want to find this fiber quasi-conformal map psi phi sub kappa. Well, here I use capital phi for kind of the QPF map and lowercase phi for the fiber map. Just let me say that the index of the invariant curve is going to be preserved under and in our process because we just consider orientation preserving homeomorphisms of the complex plane. And basically, what we are going to do is form a collection of almost complex structures in an invariant way to get the result. Like so first, I mean, here we have the first thing is if we have here this linear map M0, which recall it was just something like this. So first we want to find a real linear map, psi tilde, which kind of conjugates quasi-conformally to the map M sub kappa, which, well, I mean, we just want to change first the multiplier of the invariant curve that we are targeting to. So this can be done more easily in a left half plane. And it turns out that by the diagram, these two coefficients, A and B, which defines our real linear map, are autonomous, I mean constant. So the new Beltrami form doesn't really depend on theta. It's just something of this form depending on this fiber multiplier kappa and kappa naught. So it's just, and this is indeed not the integrating map, no? It's like, here we have this. Here we have the standard Beltrami coefficient, and there we have a collection of invariant Beltrami forms under the linear map M0. So, and then, sorry, here by invariant, I mean like fiber by fiber. Here is just trivial because it doesn't depend on the angle, but if not, we should consider like the next fiber theta plus alpha. So the next step is using the linearizing coordinates that we had before, this psi naught. Okay, so here indeed this will be like the open invariant tube, and here is just the torus product, the unit disk. And then the conics map, we can pull back this Beltrami form by these linearizing coordinates, and then we just have to, as usual, to split this Beltrami form initially defined on the tube to the whole attracting basis. Yeah, as usual, no? So here, indeed, with this quadratic family, we know that all fibers of our attracting basins are quasi-disk. So yeah, so we just have to pull back the ellipses accordingly to our map Q naught. That, remember, is just a polynomial, so it's holomorphic and preserve the dilatation of our complex structure. So and we set outside of the basin, we set the standard structure. So we just have now, I mean, we are now ready to apply like a version of the measurable Riemann mapping theorem, depending on parameters, which basically says that if the Beltrami coefficients depend continually in theta for almost every, for almost every point in the complex plane, then the corresponding integrating maps are going to be continuous in theta for all points in the complex plane. So this is, so we have just to, we have to check discontinuities almost everywhere. So for the basin of 0 and for the kind of the basin of infinity, this is clear because we have, both basins are open. So, but we may have problems in the boundary of these attracting basins. But as we've seen before, they are of 0 levels measure. So we can still apply the measurable Riemann mapping theorem to get some integrating maps that depend continually in theta. And indeed, if we choose a proper normalization, some maps psi that fix the origin and infinity, and are also tangent to the identity at infinity, we get we land to the same family of quadratic monic quadratic polynomial, which are monic and unicritical. So so we'll obtain like a new Q sub kappa with a new parameter that comes from the relation of the critical curves, and this new one has 0. Well, here I don't have a space, but it's just here we have this lambda, this Beltrami form that now depends on both parameters, and and this psi is the integrating map to the new polynomial. So we have indeed, we can check by Wells' lemma that we have indeed construct a map psi k, which are precisely the linearizing map for that new attracting basin, attracting invariant curve at 0, but now with fiber multiplier kappa. And maybe just to finish, let me go back to the fiber multiplier map kappa that we defined at the beginning. Recall that, this is our parameter, our closed curve, and here C star, maybe seen like a submanifold of this Banach space of loops with the supremum norm, and we may say that we may check that kappa is continuous by the dominated convergence theorem. And secondly, more importantly, our construction, the soft surgery construction, gives that for this simply connected neighborhood of the puncture disk, we have a right inverse lambda tilde of this form, which conjugate these polynomials, Q lambda tilde of kappa to the initial one for all parameter for all multipliers in this simply connected neighborhood. So this is, and we are working in this problem. It's look like it's possible to also have not only continuous but holomorphic dependence on the parameter, which may say more things on the multiplier map. And we'll be interested in understanding better this infinite dimensional parameter space of QPF maps, and maybe find some further analogies to the hyperbolic components of the Mandelbrot set. So this is all. Thank you very much for your attention, and come to the topics.
Have questions?
Everyone. Yeah. So I don't know if this has sense or not, but so the invariant curve that you have at the beginning that you transform as a 0, to 0.
Yeah.
Meaning in general, it is true that this invariant curve only turns once over the circle, or it could turn 3 times before closing.
Yeah, could earn more than, in the real setting, you cannot have this because, when you consider like the torus times the real line, then you cannot, the invariant curve cannot cross. But in the complex plane, we have what we call like N curves, like these are the invariant curves that make like more than one turn before closing. So, the dynamics is a little bit different, but as long as we identify like the torus with like a torus, indeed, instead of consider 0, 1, we consider 0, n, like the number of turns, then we can kind of speed the dynamics, speed the frequency variable so that we can still use the same linearization theorems and so on. Yeah.
Oh, okay, then.
At 10 to 5. And the poster section is in the room where you got those badges. So in the library.